Okay, in this video we will have a generic development of the bus admittance, the Y bus. So here you can see a generic node with the VK in the middle. They have the voltage node V1, VJ, Vn. And then you have the admittances to the reference, the YK0, YK1, YKJ, and YKN. And you can also see the current injected here and the IK going into the K node. Of course, we can have a load flow that we typically use and using then PK plus JQK into that node. And just remember that the sign of the current is of course important. So if you have a negative sign, that means it has a load, or positive is a generator. And this current IK is then the sum of all the currents that flows in and out of the node here. So then we can put up, of course, the balance based on the Kirchhoff's law. Very simple here. So the netto current we can say is YK equal, and then we have the self YK0 plus K minus V1 times YK1 plus VK minus VJ, and now is the other one, YKJ. Then you have YK1, yes, that's correct, plus then the YK minus Vn times YKn. Then of course you could, this is a generic, so you could just dotted it. It will continue to do this in all the development of, depending on how many nodes you of course is connected to this. And this again can be written as more generic, like VK YK0 plus, and then we have this summation here, J equal 1 to N. So it's N nodes, see up the left here. This is a 1. And then J cannot be K. Let's see, and then we have a parenthesis, and then we have VK minus VJ, and then we have the admittance YKJ, like this. So just instead, like you see, you have the because here we have 1, and here we have J, and have the N. So J goes from 1 to N here. And this can also rearranged in this fashion. Then we write again YEK current. Then we have the VK YK0 plus. Now we can write J equal 1 to N. And then we split up with VK YKJ minus the sum of J equal 1. J cannot be K to N. And then we write VJ times YKJ, like this. And you need, of course, here also cannot be K. And then you see this is related down here, and this is of course here. So just split it up in this fashion. So we could also define self-admittance in this fashion, this YKK, that means all impedances connected to admittances connected to the node K. That means YK0 plus the sum, and the same j equal k, and cannot be the same as k to n, and then we have y k j, like this. So here you can see now we could rearrange it and put it here. We also actually found out that this y kj here had also be defined a little bit different. It should be like if you have y kj, should actually be assigned, let's see, as minus kj. So it should have an opposite sign when you use it in the calculations. So let's look a little bit more on that. If we assign this as 1, maybe this as 2, and this 3, and this 4, so you can identify them. Then let's look further on this. So you can take it maybe up here. Let's take 4 into 3, just some see some connections here, and then we can express it like this. We can have the current now we're written as vk parenthesis the yk minus ykj. That comes then from 4 here. So just to rearrange, this is number 4 here, in here, instead of this yk0. And then plus, let's see, we had to have the vk ykj minus vj ykj. And we can go further, and then we get yk k ik, then we multiply vk ykk minus vk ykj plus vk ykj minus jykj, and then this goes away. We then are sitting with the yk equal the yk ykk minus 3j ykj, like this. And then we know this sign should be opposite, so we will then have a plus here to make the assignation correct. Or in general form, vk equal ykk plus summation, then the same as before, equal 1. Cannot be k to m, then we have j ykj. Yes. Let's now finally then write up with in the matrix form. Let's see. We can have it like this. Equals. And we have the I1, IK, and IM. 3 currents. And then we have Y1, 1, y 1 k, y 1 n gives the voltage v1. Okay, let's see. Take it once again. E1. And then on the same for second IK is YK1, YKK, and YKN, VK, and for the current IN, YN1, YNK, and the YNN can be written as V1, like this. So every row is then the sum of the currents in the node, and so remember that. And then we have this is then written as the current bus equals Y. Let's see. Y, Y, and then Y V bus. And it can be solved. The variables V bus is equal the inverse Y minus 1 and the I bus. So to sum it up, we can say that the YKK is the sum of all Y's connected to the node K. So and the YKJ, so the self and but now the YKJ is the negative Y to the line connecting node K. It is also symmetric then along the diagonal on this here. And many elements in this matrix is 0, since every node is only connected to a few other nodes. We are seldom talking about the current flow, we're more talking about the power flow equations. So this is important. And we also call this here the compact form of the matrix form above here.